Now let's talk about a few paradoxes that arise in probability. Um, the reason we talk about those paradoxes is just to show some motivating examples, but also to show how counterintuitive um, probabilistic calculations can be sometimes. So we'll start with an envelope paradox, and the setup, also known sometimes as an exchange paradox. And the setup is the following. A Swami puts $M in one envelope and twice that size, 2M, in another envelope. So you have two envelopes, and one envelope has $M in it, and another envelope has $2M in it. And he hands envelope to you and one to your opponent. The amount are placed randomly, and so there is probability of 1/2 that you get either of those envelopes. You open your envelope and you find that there are $X there, and let Y be amount in the opponent's envelope. And so what you really don't know whether Y equals to 2X, so either your opponent has the double, or Y equals half of the X, so your opponent has the envelope with smaller amount of money. And you know that again, Y is either half of the X or twice the X, and you're thinking whether you want to switch the envelope. And it's tempting to do these expected calculations, expected value calculations that go as follows. So with probability 1/2, the opponent has half the money, so 1/2 of the X, and with probability 1/2, your opponent has twice the money. And if you calculate expected value for the random variable Y amount of money that your opponent has, then you have 5/4 times X, which is greater than X. Then utility tells you basically to switch. So there are more money in your opponent's envelope, which of course doesn't make sense if you just think about this using common sense. And these simple calculations of expectation tells you that you always have to switch. And consequences of this, following the logic of backwards induction, that even if you didn't open your envelope, that you would want to switch. And of course, it's relatively simple to fix these calculations and think about the problem in a slightly different way. So you can think about this way. So if you switch, um, um, there is a half uh, probability that you gain X, so you get X, and there is a 50% chance that you lose X, so minus 1/2 times X. Okay. Um, so what you basically get is your expected gain out of the switch is 0. So expected gain from switch. Right. So okay. So that's you can do also this expectation calculations and get a reasonable outcome. But another way to resolve this paradox is to use the Bayes rule. And again, there is no really way to say whether you have to switch or you don't have to switch. If you just use the basic rules of probability or common sense, then the conclusion is there is no need to switch. However, however, if you have some prior knowledge about the amount of money that you think Swami placed in the envelopes, then opening your envelope and learning what was the value in your envelope can tell you something about the value in the envelope of your opponent, about the value of Y. So, and it basically boils down to this ratio. Let's talk about this. So instead of using this unconditional expectation, we're going to use the conditional expectation. we're gonna calculate the expected value in the envelope y is the probability that y given half of an x times x, and then again the probability, the outcome of this event is that he has half of the x in his envelope, and the probability of y given 2x given x times 2x. And we can use the Bayes rule to calculate this value. So what we want to calculate p of y given, for example, 2x given x, and it's just going to be a joint probability p of x and y divided by the marginal p of y. So to do this type of calculations, you have to make an assumption about this joint probability of p of x and y. And let's say they are, let's do an example. Let's assume that the amount of money Swami puts into envelope follows a Poisson distribution. And here's the density function that it follows. And let's say it's centered at 10. So 10 is the expected value for the amount of money Swami puts in either X or Y envelope. And let's say you open your envelope and you find that you have $6 there. Then probability that your opponent has twice this amount, which is 12, is quite high. And the probability that your opponent has half of this amount, which is 3, is very low. So in this case, if you open your envelope and you assumed this Poisson distribution to be the prior distribution over the amount of money being put in each of the envelopes, then of course you switch. So under this scenario, you switch. Okay, but let's say you open your envelope so again, you have distribution centered at 10, and you find out, let's say that you have $18 in this envelope, then half of this is 9. It has very high probability, and twice this amount is 36, has very low probability. So in this scenario, you do not switch. So the morale of this paradox or this calculations is that if you can formulate some prior distribution, and we call it P of M, prior distribution, over the number of dollars to be placed in the envelope by the Swami, then actually the information that you gain from opening your envelope can be used to make the decision of switching or not to switch. And then you just have to calculate the expected value of the other envelope and the condition that as long as this expected value is greater than X, then you just switch. Let's talk about another example, which is called prisoner's dilemma. There are 3 prisoners, A, B, and C, and each believe are equally likely to be set free. So each thinks their probability of going back home is 1/3. And let's say the mayor just pardoned one of them, and they don't really know who got pardoned, and they make this prior assumption, 1/3. But prisoner A goes to the warden W and asks if she or he is getting axed. Warden cannot tell A anything about him, and warden tells the following piece of information: B is to be executed. Now, what A wants to do, A wants to take this piece of information and update the probability. A wants to calculate the posterior probability of being set free given the piece of information given by the warden, WB. And we're going to use the Bayes rule for that. It's the probability that warden gives this piece of information given A is to be set free times the probability that A goes home divided by the total probability of this piece of information. And to calculate the total probability, we're going to use our formula that connects the total probability and joint. So we just sum up the joint. It's the probability that this piece of information is given A goes home times the probability that A goes home, plus probability of this piece of information given that B goes home times the probability of B going home, plus the probability that Warden talks about B given that C goes home times the probability of C going home. Well, we know the price. Price is 1/3. So 1/3 here, 1/3 here, 1/3 here. Now let's think about the conditional probabilities. Probability that Warden says B is to be executed given A is to go home. Well, Warden cannot say to A anything about A, and Warden either has to say about C or B. And in this case, we assume that Warden doesn't have any preferences. He just randomly picks B to talk about. So the probability that Warden talks about B is 1/2. Now let's think about this probability. The probability that Warden talks about B given that C is to go home. And in this case, if C is to go home, if Warden tells something about C, meaning Warden says C is to go home, that A will know right away that A is to be executed, meaning that the piece of information about A has been conveyed to A himself, which is against the rules. So Warden cannot talk about C being freed when C is actually to go home, but Warden also cannot talk about A, because it's again, that's the rule. So Warden must talk about B. So probability that Warden says something about B, says B is to be executed given that C is to go home is 100%. So this is probability 1. And so this is 1/3. So what we have on the top, we have 1/2 times 1/3, 1/6, and at the bottom we have, sorry, this is 1/2. So we have 1/6 plus 1/3. So this is 2/6, this is 3/6. So this is 1/3. So we have 1/6 divided by 1/3. So it's 3 divided by 6 or 1 divided by 2. So meaning that the A, you remember the prior was probability A of going home is 1/3, and we use this piece of information that provided by Warden to update the probability and calculate the probability of A going home given the piece of information provided by Warden. And now we update probability to 1/2. Now you can pause this video and you try to compute probability that C goes home given that Warden given this information. So let's say C overheard this conversation, and the question is, should C get excited or not really? So try to do those calculations yourself. Let's do a final example of this sort. This is a famous Monty Hall problem or game show problem. It's named after the long-running TV show Let's Make a Deal, and Monty Hall was the host. So the setup is the following: you have 3 doors, and the participant has to choose one of the doors, and there are 2 doors that have goats. I'm not gonna try to draw a goat, so I'm just gonna write goat. And another has a car. So car is available price and goat is worthless. And what happens, participant doesn't know which door has a goat, which door has a car. Participant picks a door. So door is numbered 1, 2, and 3. And then what host does, host opens another door. So let's say you pick door number 2, and the host will open door number 1 show that there is a goat. So host will never open your door, so will never open door number 2, and host will never open door with a car. So host will open door number 1 if you picked 2, and then host would ask you whether you want to switch or not. And the conclusion is somewhat counterintuitive. The correct answer is that yes, you have to switch. And you can use imaginary example. I think my favorite way to explain it is when you have, let's say you have 1,000 doors, and let's say you pick one of the doors, and then host will open other 998 doors for you, showing that there are goats behind those, and then host will ask you whether you want to switch or not. In this case, the answer is relatively clear. You know that the door that hasn't been opened by the host has car behind it, more very likely. And you, of course, you want to switch. But with 3 doors, it's the calculations are not intuitive, and our brain doesn't process them well. But we can try to again apply the Bayes rule here and do those calculations. So let's look at the following sequence of events. So let's say you pick door 1, and we say that's event x1. And then let's say that host opens door 3. So what then we want to know? We want to know the probability that the car is behind door 2. So we're going to call this event C2. C2 is car behind door number 2. Given the piece of information that you know that you opened door 1 and the host opened door 3. So let's use the Bayes rule to calculate those. So again, we want to calculate probability of a car being behind door 2, given that you pick door 1 and host opens door 3. And we're going to use the Bayes rule, so it's the probability of host opening door 3, given that car is behind door 2 and you pick door 1, times the prior probability of car being behind second door and you pick in door 1, and divided by the total probability of you picking door 1 and host opening door 3. Okay, and we can write this one down as probability of host opening door 3 given x1 being picked times the probability of x1. And at the top here, probability of car being behind 2 and you picking door x1 are independent events, so it's just the probability of car being behind door 2 times the probability of you picking x1. So we actually can cancel x1 here and here. And so what we have at the top, we have probability of host opening door 3, given that car is behind 2 and you pick door 1, times the probability of car being behind door 2, divided by the probability of host opening door 3, given that you picked x1. Now let's see if we know those. Well, we need know this one. The probability that car is behind door 2 is 1/3. So we assume that show organizers randomly pick a door, so there is nothing special about this. And probability that the door 3 is to be opened, given that you pick door number 1, is 1/2, because the host cannot open your door, so host can either open door 3 or door 2. So with half probability, door 3 is to be opened. Now let's think about this value. Probability that host opens door 3 given that car is behind door 2 and you pick door 1. So we know that host cannot open your door and host cannot open door with a car. So in this case, host must open door number 3, so probability of this event is 1. So what we have here is 1/3 divided by 1/2. In other words, it's 2 divided by 3. Okay. So again, your prior probability of picking the car, pick the correct door, was 1/3. So you just randomly selected 1/3. And you use the piece of information that door 3 was opened by the host to update your probability of picking a car. Of course, you have to switch in this case because the probability of car being behind the other door is 2/3 now. But you update your probability of picking the car, and it's equals to 2/3 now. So you double your chances of winning a car by switching.